Hello and welcome to lesson 5.1, 5.2, rates of change and the number e and the natural logarithm. What I would like you to do is make sure you have this video paused and go onto the Desmos application. There should be a Desmo link in the same lesson for you, and I want you to try finding the derivative of these different functions. Some of them you might have to turn on and figure out. The value b has to be any value between the numbers 0 and 1, and once you do look at the derivative, just try to find the derivative of y equals b to the x and adjust the value of b until you get the function and its derivative to be the exact same thing. What you will notice is that the derivatives are going to be exponential functions as well. So pause the video and do that now. Okay, moving on. So, what you might have noticed is if you find the function f of x as b to the exponent x, then its derivative turns out to be k times b to the exponent x, where this value k is some kind of real number. It's going to change depending on what the base value is. If the base value is above, I think it's about 2.8, 2.9, then the k value is going to be above 1. If it's less, it will be between 0 and 1, and if your base value is actually a value between 0 and 1 itself, your k value will be a negative. So what you found was the derivative of any exponential function is also exponential, which you can see based on this. So, what you might have noticed as well was when you tried to make the base function equal to its derivative function, you found that you got closer and closer to a value called e. This is approximately the value of 2.72. What's so special about this function? Well, its function, if it was the function f of x is equals e to the exponent x, then its derivative is also e to the x, which is a great function to know and to find the derivative of, because it's a very easy derivative to calculate. This exponential function that we create here, e to the exponent x, is called the natural exponential function. Now, just like any other exponential function, there is a logarithm that goes along with it. So if your function is y equals e to the exponent x, we call the logarithm of that same base value y equals ln of x. It's improper form to use log to the base e of x, but we will still know what you mean when you do so. It's just improper form. Because the previous one was called the natural exponential function, this one's called the natural logarithm, and follows logarithmic properties. Just like you can, the values of x in this case for the logarithm are real numbers, such that x has to be greater than 0. You'll also notice the range for this is y belongs to every real number possible. Okay, so some other things to notice. Since it is also a logarithm, it also follows other logarithmic properties. So, if you have ln a plus ln b, that's the same as, calculating ln of a times b. If you have ln of a minus ln b, that's the same as finding ln of a over b. If you have ln of a to the exponent p, you can rewrite it as p ln a. And if you ever wanted to use a change of base formula for a logarithm, you can use a natural logarithm x over a natural logarithm a to calculate this. So let's look at some properties and some values that we can calculate with this. So we're going to solve for the values of x using exact values. In other words, we're not going to approximate them using a calculator. So to get rid of e, you have to find the inverse function. the inverse function of e is your natural logarithm. So we're going to place a natural logarithm on both sides of this expression. That'll cancel out the e and leave you with just 2x minus 5 is equal to the natural logarithm of 10. To solve for x, I gotta add 5 to both sides. And to solve for x, I just have to divide both sides by 2. So this is how you'd write that as statement. You can also write it as 5 plus ln 10 over 2. Okay, likewise, we're going to try to get rid of the ln here. Well, the inverse function of natural logarithm is e. So we raise both sides to the base e. That'll get rid of this e and ln together. That just leaves us with x plus 2 is equal to e to the exponent 8. And then solve for x. E to the 8 equals, x is equal to e to the 8 minus 2. Okay, so let's try some others. To solve anything like this, best option, try to solve it or create it, isolate it to be an exponential. So I'm going to divide both sides by 10 here. So this gives me 3 times 3 equals 2 to the exponent x plus 1. Now to isolate for x, I'm going to find the natural logarithm of both sides. Based on one of the properties I know, I can bring that x plus 1 down. Now I can expand that right-hand side to be x ln 2 plus ln 2. This side is ln 3. To solve for x, bring the ln 2 on the other side. And then I divide both sides by the natural logarithm of 2. Okay, the last one. Find the natural logarithm of both sides. Again, bring the 7x down. To solve for x, we divide both sides by 7 and the natural logarithm of a half. So ln of 3/5 over 7 ln of a half. Now they don't usually like to have you have fractions within the natural logarithm, so I'll have you change it to the other format shown right here. So this is going to be the natural logarithm of 3 minus the natural logarithm of 5 over 7 times the natural logarithm of 1 minus the natural logarithm of 2. If any of you remember anything about your logarithms, any natural logarithm or logarithm of 1 just turns out to be 0. So this is just ln 3 minus ln 5 over negative 7 ln 2. Or if you prefer, ln 5 minus ln 3 over 7 ln 2. Let me fix that too. And there we go. Thus finishes our lesson.